Hey there, welcome back again to AR to the rescue. In our journey to gravitational waves, this is our first video on neutron stars. So before we get forwarded towards the video, just make sure you subscribe my channel and push the notification button. So are you ready for our neutron stars video? I'm sure you are. So let's get started. Gravitational waves are making news today. 100 years ago, Einstein, based on his general relativity, proposed that something like gravitational waves should exist. The theory was simple. Just like electrons on acceleration emitted electromagnetic waves, mass on acceleration should emit gravitational waves. Now the question was about its possibilities. Earth and Sun orbit around each other, but the gravitational waves emitted by them are feeble. Also, the motto of finding gravitational waves was to know the happenings in the far universe and to detect them. The gravitational waves which are supposed to be emitted by them due to their cataclysmic nature should reach Earth. Now Earth is not being affected much by these waves, so if they are coming, they should be feeble. Now to travel such a large distance of millions of light years, at the origin point, gravitational waves have to be powerful. For them to be powerful, the mass of the emitting body should be much high. This result suggested that neutron stars should be contributors to gravitational waves. This is because neutron stars have got collapsing nature. Their mass has got concentrated towards the center. They are a dense piece of matter. Size very much small, mass about 1.4 times that of Sun. The possibility of neutron stars emitting gravitational waves comes from an event of merger. However, today we don't have evidences for a merger, but we do have some info about inspiral, and that's where we have found gravitational waves successfully. The whole theory is that two neutron stars, because of gravitational pull, can come closer and orbit each other. During orbiting, if the system is asymmetric, it will emit gravitational waves. Both stars, while orbiting, will come closer to each other. This event is known as inspiral. They will continue orbiting each other, and at last they will merge. This event is known as merger. During a merger event, there is a peak of gravitational waves emission. However, we don't have evidences of gravitational waves emitting from a merger. Moving on to the name of neutron star. Why they are named so? Obviously because they are made up of neutrons. But the neutrons come from the fusion of protons and electrons. We know that they have got a collapsing nature. Their mass gets concentrated towards the center. Now according to conservation of angular momentum, because of its concentration of mass towards the center, the speed of rotation increases. It has got 20 to 30 billion times more gravity as compared to Earth. This indicates the density of neutron stars. According to an estimate, a teaspoonful of matter from a neutron star would weigh billions of tons. To visualize, it will weigh more than the total cargo carried by all the trucks globally. Even though the mass of neutron stars gets concentrated more and more towards the center due to gravitational pull, it has got a limit. Further collapse is prevented by neutron degeneracy pressure, described by Pauli's exclusion principle. Now, what the heck is this? For any main sequence star, the reactions driving it are the fusion reactions. Three fusion reactions of hydrogen isotopes produce a large amount of energy. Fusion reaction of deuterium gives 3.3 mega electron volt energy, which is a large amount of energy and can be almost an unlimited source of energy on Earth. These reactions are as follows. I can't speak them, but they produce neutrons. The funda of fusion reactions is that smaller nuclei fuse to form heavier nuclei, a complete reverse of fission reactions. Thus, in a star, fusion causes the core to be accumulated by heavier nuclei up to number 26, that is, iron. Here, depending upon the mass of the star compared to Sun, which is also known as the solar mass, further reactions can take place. In a main sequence star with about 1.39 solar masses, the electron degeneracy stops further collapse of matter. That's where iron gets accumulated towards the core. The 1.39 m limit is also known as Chandrasekhar limit. The fact is that Subramaniam Chandrasekhar in 1930, at an age of 19, derived this limit. That was not accepted officially at that time, though at the backstage, but not officially. It was because, if true, it would allow the existence of black hole, which at that time was not possible. How black hole now? Because if the mass of a star was more than 1.39 m, electron degeneracy gives up. Electrons get captured, they are converted into neutrons. Now there's another limit where the neutron degeneracy too gives up. And that's when the star gets converted into a black hole. Now we stopped by neutron degeneracy pressure, which, as I said, is described by Pauli's exclusion principle. The principle says that all electrons can't remain in their same low energy states. There should be energy bands. Now, as the core gets studded with heavier nuclei, energy goes on building up according to mass-energy relationship. This energy is taken up by the electrons, which move over to their higher energy levels. Now, the increase in the gravitational pull of neutron stars is explained by this studding of the core with heavier nuclei. The reactions continue, the buildup of core continues, and the electrons move on to their higher energy states, and the electron degeneracy pressure increases. Now, if the mass of the star is greater than 1.39 m, then because of further increase in electron degeneracy pressure, the electrons are captured by the nucleus, where they combine with proton to form neutrons, along with tremendous amount of neutrinos. And further, as I said, the collapse of neutron stars is prevented by neutron degeneracy pressure. Now, just like Chandrasekhar limit, neutron stars too have got a limit, which here we call the Tollman-opneheimer-volkoff limit. It has got boundaries at about 3 solar masses, that is 3m. Now, before the neutron stars get converted into a black hole, there are some intermediate mass stars. They can be high mass white dwarfs or low mass neutron stars. Between 3m and 5m, intermediate mass stars like quark stars and electroweak stars have been proposed, but none of them showed up to prove their existence. Beyond 10m, the stellar remnants of neutron star will be converted into black hole. However, the smallest observed mass of a black hole is 5m. Now, rounding up, the neutron degeneracy is same as electron degeneracy, the stellar application of Pauli's exclusion principle. Here, no two neutrons will remain in the same state. The neutrons take up the energy and occupy all energy levels, thus preventing further gravitational collapse and keeps the star a neutron star. If the mass of the star is more than 3m, its neutron degeneracy pressure will give up, giving rise to the black hole, and of course including the intermediate mass stars. That's about neutron degeneracy pressure. Moving ahead, they've got a surface temperature of 6 into 10 raised to 5 Kelvin. Now this is a consequence of fission reaction, I suppose. Because thinking that way, how nuclear reactor works. They carry out fission which supports fusion, because fission increases the temperature to that much Kelvin. We now know that neutrons and neutron stars are formed by electron capture. The gravitational collapse for a star which with mass more than 1.39 m, pushes electron into nucleus, where it combines with the proton to form neutron and neutrinos. They give out the neutrinos and the matter surrounding the dense core. A schematic diagram of the process shows the initial main sequence star stage. It has got an inner core and a massive star. In the second stage, outer layers begin to collapse onto the inner core. The violent process leaves a contained shock wave. Third one, the matter of infalling layers compress and merge. Fourth one, the convection results. The fifth one, a shock wave is released, and at last, the core, a neutron star. This was just a sneak peek into the formation of neutron stars. Just stay tuned on our journey of gravitational waves and we will find more amazing truths. So, goodbye for now, stay tuned, and thanks for watching.